Hello everyone, welcome to Group D's presentation, and today we will be discussing the wind turbine gearbox design. The gearbox should be designed to transmit a 1 megawatt power throughout the stages of the gearbox, and the input shaft should rotate at 20 RPM with an output of 1800, and it should be able to generate 1 megawatt of power. Now let's start with the loading and bounding conditions. So the loading and bounding conditions we start with the torques on each shaft. The main shaft is that rotates at 20 RPM, has been found to have torque of 4,231 kilo-pound-force. Now the formula to calculate the torques was H equals to T by omega. Omega, which is rad per second, and H, which is the power in watts, and T is the torque force. We can do that for the intermediate shaft. Since our gear ratio is 10:1, we can find the RPM as 200 RPM for the intermediate shaft. Therefore, we're going to have a 416 kilo-pound force for the torque force on the intermediate, and on the final, we will have 1800 RPM with 47 kilo-pound force for the torque force. Afterwards, another boundary condition and another loading condition that we have is that the degrees of freedom. The shafts should, the different parts will have different degrees of freedom. The shafts should have 1 degree of freedom, which is the axial rotation of the degree of freedom, which is 1. And then the gearbox should have 0 degrees of freedom, as it has to be fixed in the house plating and that it shouldn't move from its position, only for maintenance and etc.
Hello, my name is Christopher Enriquez Birch, and in this part of the presentation, we'll be going over the gear selection process. First, we want to ensure that we choose the proper gear ratio. This is done in order to minimize the size of the entire gear train. In the second part, we want to go over meeting the safety standards. We want to ensure that all the parts will operate safely and that they won't fail. And third of all, we want to save costs. We want to ensure that we aren't using unnecessary materials and having an unnecessarily high strength for a part that is only subjected to low stresses. We wanted to ensure that we would minimize the size of the gear train. In doing so, we want to use the ideal gear ratio equation, which would consider that the first stage and the second stage are equal. This would give us a value of 1/90, which was the gear ratio, and would give us an ideal value for the scaling of both stages to be 1.94868. This is not possible to have an even amount of teeth, so we have to use the next two best values, which would be a scale of 1 to 10, followed by a scale of 1 to 9. So this would then allow us to scale from a 20 RPM all the way up to 200, and then the 200 mid shaft would then scale up to 1800 RPM. In doing so, this would minimize the total size, as the gears would in turn cause less overlap on the outside terms, as the ratio are as close to possible as the ideal gear ratio. In order to ensure that we meet all the safety standards in our parts, we need to consider the amount of stress that the first stage is dealing with. As we know, the input transmitted load is going to be significantly higher in the first stage than the second stage. We need to ensure that we select the right properties such as materials, diametral pitch, and face width to withstand this high stress. Choosing the diametral face width to be a smaller value will lower the amount of transmitted load, as this will increase the pitch line velocity that the part will be so the gears will be subjected to. In doing so, we also want to choose the strongest materials possible in order to ensure that the strength of the part is greater than the stress. As you can see here, this was part of our design process in the gear selection, and we chose the strongest material possible. And we found that at the strongest material possible, with a diametral pitch of 2 inches, we would need a face width of 16 inches in order for the first stage 20-tooth pinion to withstand the stresses that it's applied to. But in doing so, we also realized if we chose the same face width for the second stage, due to the fact that this shaft is at a significantly lower transmitted load, we found that there would be a lot of unnecessary safety factors and therefore cost loss. So in order to reduce the cost that our gear train design would impact, we wanted to minimize the variables in the second stage of the gear train design in order to ensure that the safety factor would still reach a required amount, but it wouldn't be unnecessarily high. In doing so, we iterated the size of the face width for the second stage all the way down to 5 inches, and in turn we also were able to change the material that we chose from grade 3 all the way down to grade 1. And in doing so, we were able to reduce costs in terms of the material used as well as the cost of the material itself, while also still reaching the safety factors required.
Hi, my name is Matthew Doyle, and I'll be providing an overview of the wind turbine gearbox shaft designs. I'll be discussing the performance characteristics of the shafts regarding the critical speed consideration that went into the designs, the ability of the shafts to withstand the applied loading of the wind turbine, and their lifetime or fatigue characteristics. Beginning with critical speeds, it is important to note the role that they play in determining the geometry of the shafts. They were taken into consideration to ensure the shaft remains stable throughout their intended range of operation. As can be seen in the table below, each shaft possesses a required operational speed according to the gearing of the system. All shafts possess a minimum shaft diameter greater than the value shown in the fourth column of the table to ensure the first critical speed associated with the shaft diameter is greater than twice the operational speed. Thus, the shafts are designed to not suffer from any associated vibrations or deflections. So moving on to the yielding and fatigue behavior, the table below shows that all shafts possess minimum fatigue and yielding safety factors that are greater than 1.15. In terms of yielding, this ensures that the loading would have to increase by 15% before yielding may occur. As well, by having the fatigue safety factor greater than 1, the shafts have been designed according to D.E. Goodman failure criterion to withstand greater than 10 to the power of 6 cycles, recognized as having infinite life. These characteristics make the shaft designs fully capable of functioning as desired for facilitating the power transfer necessary to generate 1 megawatt of electricity. Moving on to the physical drafts of the components, all shafts are designed to minimize mass and to ensure the design is cost effective. The shafts are machined from high-strength AISI 4340 steel. The input shaft can be seen to have an overall length of 32 inches and possesses an 8-inch extension from the gearbox housing for the purpose of coupling to associated components. The intermediate shaft is shown to have a 52-inch length and possesses a step design similar to the input and output shafts. The step design allows for the bearings and gears to be easily and accurately located onto the shafts. All shafts possess steps that ensure the gears are mounted in line with one another to ensure full meshing and no undesirable offsets. As can be seen with the output shaft mechanical drawing, all shafts were designed to reduce mass where necessary while abiding by required safety factors. As the output shaft possesses a substantial drop in torque, it requires less material and thus the mass and cost have been reduced in this component. This shaft also possesses an 8-inch extension from the output side of the gearbox for it to be coupled to the shaft of an electrical generator.
Hello, my name is Matteo Masciantoni. I will be discussing the results from the modeling both in the preliminary and final designs. I will be talking both about the implementation of the iteration changes and the final shaft and final design models. These are two of the shaft models, the input and the intermediate shafts, with the preliminary designs being on the left and the final designs being on the right. For the input shaft, multiple things were changed in the iterations. We realized that while the diameter of the shaft had to be increased, we were still able to reduce material in the size of each step so that we could still reduce cost, thus achieving our objective. And for the intermediate shafts, we realized that although some diameters had to be increased, we were able to reduce a lot of other parts of the shaft. So the gear changed thickness, and there's a large section of the shaft on the left, the current way that it's viewed, the left part of the model, that is was allowed us to save mass because the gear step didn't need to be that long. This was also seen in the output shaft as that gear also changed, which is right here. The output shaft preliminary design versus the final design. The ends are where the shaft will go out, so those are a little arbitrary. The important parts are closer to the right of the shaft on both sides, and as can see, the step had to be greatly increased. The size of that first step had to be increased due to the diameter being decreased from our iterations. This was the shaft that actually saw the greatest reduction of mass due to the critical speeds being the quickest. We were somehow able to make this one the thinnest, and that was just all due to gear ratio and the critical speed calculations. So with the original designs, our preliminary designs had these big bulky gears and attached to these windows, these walls over here, and there is the shafts attaching just simply with a 1 to 10 and 1 to 9 gear ratio, and that was then modified to this. As you can see, it's a lot less bulky. These are two separate, the one all the way to the right and the one all the way, sorry, the one all the way to the left and the one right beside that. Those two models are just different views taken from the front and the back. And then the top view here, you can see in comparison, they are much thinner and they are much less bulky. Thank you.